Do you
Yeah.
want to introduce yourself or should I introduce you?
Yeah, it's fine. So welcome to the 12th week of the Categories reading seminar. Today I'll be talking about homotopy groups of time complexes and the long excel sequence of vibrations. So basically, try to encompass the last two sections of third chapter, Cisinski. And this time it will be a bit it'll be kind of rough and not so fine. So yeah, I won't be proving a lot of things, but for time purposes. But yeah, so yeah, let's begin. So right, so yeah, I'll be using Lury's notation throughout. So everything more like all the notation from Kev down. Right. So okay. Well, so here's the plan. So first I'll be talking about homotopy groups, spatial sets, and then I'll talk about pointed complexes, and then the connecting homomorphism and the long exact sequence of vibration, and then I'll be just briefly talk about fully faithful essentially surjective functors and the infinity lag. Right. So, right. Can you pause the recording for a moment? Sure, we're back. So, okay. So let me start this section. So I'll be talking about homotopy groups and begin. So this will be really elementary. So yeah, I won't spend much time on elementary stuff, which means that yeah, I won't be moving a lot of things as I said before. So yeah. Right. So yeah, beginning with the fundamental group part. So the fundamental group part of a Khan complex. So the part X is its homotopy map. And we'll denote it as follows. Right, as I said, Lury's notation, which is what I'll stick to. Okay. So, right. So now, okay, now let's talk about the fundamental group construction. So for each point. So yeah, so let's denote. Yeah, we denote this automorphism group. So yeah, that is precisely the fundamental group. Right. Which is, so I'm going to add this, which is the fundamental group of X with respect to the base by small x. So yeah, so we note that yeah, I don't need anything. So for all maps that you have, so we have maps in between Khan complexes. We have an induced map, right? We have induced maps. So okay. So without further ado, let me define homotopy groups. So I'll be working with So I'll first define homotopy groups for vibrant simplicial set, and then after some time I'll define I'll talk about what homotopy groups of Khan complexes. Let's first start a bit more general. Homotopy groups. So X is a vibrant simplicial set, and take an object. Then we associate sequence of sets. Right, and define the homotopy groups recursively. So for n greater than or equal to 1, so it is the set of homotopy classes of maps. Right, relative to the boundary. So yeah, the notation that's used in the simplicial homotopy form, there is thing by Goes and Jardine. So yeah, so they write use this. Right. Says that. Okay. So this is the set of homotopy classes of maps relative to the boundary. Says that which fit. So that fit into the following diagram. So let me show this. Right. So right, yeah, there is some abuse of notation, but it's typically custom to do so. So this is the map alpha that we have. We generally call this map to be alpha. Right. So just a composition. So just compose alpha of the equation. So sometimes this map is just called alpha, the composition. Right. Then we define of x to be is the set of homotopy classes of vertices x. Right. So yeah, maybe for a mark. These are generalizations of the fundamental group that we saw. So for n is equals to 1, we get back the fundamental group. Right. That we defined earlier. And so, okay, now let me. So, yeah, this is a remark. We'll talk about this later. So, okay, suppose you have a configuration. So this is the way you get a long exact sequence of homotopy groups. I'll just be mentioning now that I'll talk about it in detail later. It's a configuration in Khan. So yeah, I'll talk about the point of writing using this notation. So turns out we'll be talking about pointed Khan complexes that I talked about before. So we also will be talking about configurations in the category Khan pointed Khan complexes. Can be pointed Khan complexes that do not affect this. So just by the start. So that is right. So it is a configuration in the category of Khan complexes. And right. So suppose A is and if A is equals to B, then yeah, denote the fiber of F over the vertex B by, so this is our notation. And then this is exactly the notation that we found here on. Right, so this is my fiber. Then we have the following long exact sequence. So let me try to write this. So yeah, define this one. Oh, okay, my bad. We'll try to put this line. Right, I will get such a long exact sequence. So, okay. So theater, again, I will be proving it. So this is based on the fact that, so I think, yeah. So I think that I had said before that we can associate a sequence of sets. So it turns out these sets are a group structure. And that's why we call them multiple groups in the first place. Let me drink some water. Yeah. So, okay. So talking about the group structure. And this group form. And in fact, it's abelian as well for a greater. So yeah, I will be doing this. So yeah, but the way to try and work this out would be using loops, loop spaces, right? So just have so you can show that when you can this show that have this and then focus and prove that you have a good structure. Yeah, I am. Yeah, I'll be skipping the details. So okay, so now when we begin talking about pointed cloud complexes. So why do we need pointed cloud complexes? Yeah, but first let me start with the definition. So a pointed simplicial set, so starting with simplicial sets, is a pair where we have a simplicial set X and a vertex. This is a vertex of X. If X is, so let me write, X belongs to the category of complexes, then so it is a pointed, so this is PT, that means pointed, so it fits this way, So then it is a pointed complex. So we get we get a category of pointed complexes. So we have I don't know if this is the right way to say this. We have categories. So we denote this category as follows. So right, when the objects are so these pointed complexes that I defined before, right? So stuff like this. And morphisms, so morphisms. So again, there's an abuse of notation, so this morphism, so it's generally it's follows. So as I said before, so as I pointed out before here, yeah. So I say that it is a configuration in Khan. So because even if it's a pointed Khan pointed configuration, we just call it a configuration in the category of pointed complexes. saves a lot of time. Right, so this is the way we denote it. So it is just a map. So it is a map from X to Y. So we add here denoted as. Right. Is a map such that it takes X to Y. Okay. So in order to define the group structure of so yeah, we restrict ourselves to working with pointed non-complexes to the structure of the groups that we have seen so far. So because of the space point that we are fixing, right? So in the definition we are fixing the space point. So because of that, it kind of is. So it is more of like an it is kind of a construction that we do in order to comfortably work with the groups. So, right, so for the group structure, so let me define a few things. Again, so most of the treatment, as I said, because it is find that in Paragon. Most of them novel and new. So first you take a simplicial set and a simplicial subset, subset. So otherwise a simplicial subset is a summand of X if X Z or some simplicial subset of X. Right. So what I mean when I say simplicial subset is a summand of simplicial set. Now let me define connectedness in the context of simplicial sets. So everything, it's like everything that you will be seeing, we are working on. So it is kind of natural in the category of multiple spaces. Yeah, so it is a good. So we will see like everything is right. So it's almost identical. So for a simplicial set X is said to be connected if first it's non-empty and the summand it has is either empty or X itself. So it's kind of in line with the notion of connectedness that we have for topological spaces, the fact that we don't have a separation, right? So, right, so now let me define connected components. Connected components. So again, you take a simplicial set and our simplicial subset is called connected component. Connected component if Y is a summand of X and Y is connected. Right, so that just means that Y is non-empty, and if Y has, and the summands of Y are either empty or Y itself. Right? So that is what I mean by connected components. So now, how does the pointed homotopy category of complexes look like? So, yeah, that is what we'll be talking about. The pointed homotopy category. Pointed, fine. So it is. So the pointed homotopy category of complexes is the homotopy category of pointed complexes. So again, so you take pointed simplicial sets. So, right. So for pointed maps, again, these are pointed maps, but we denote them like any maps. For pointed maps. So So F is pointed homotopy. Sorry, is pointed homotopic. So we denote this as follows. AKA F is pointed homotopic. Right. So what I mean by pointed, as I said before. Right. If they belong to sorry, no one. If they belong to the same connected component of the binary, and I'll be defining it. I'll be doing notation for this. You can kind of see why I chose this can be like a version of the homotopy, right? So it is just a pointed version, it's not very difficult to understand, right? Okay, now, so this is what I mean when I say two maps are pointed homotopic, right? And now I'll also define what a pointed homotopy is, and then I'll kind of relate both of them. So pointed homotopy as a map, so I can stick to that. So a pointed homotopy from F to G has some opposite. So now, right, says that interest rate is equal to 0, so it becomes F and G. So this is just just a pointed version, it's not a big deal. Wait, it's supposed to be H. Okay. Okay. So now relating model. Or again, we take pointed simplicities. And we take these pointed morphisms. So if this pointed homotopy to G, if there exists a sequence of pointed maps, right, such that so okay, let me so okay, let me name these maps. So HF is equal 0 goes up to HN, which is our G. Such that so there exists a pointed homotopy from Fi minus 1 to Fi, or from Fi to Fi minus 1. So yeah, so then so if Y maybe instead of a remarkable consequence rather. So if Y is a count of X, right, so then F is pointed homotopy to G, if there exists pointed homotopy from F to G. Right. So yeah, this is what I had said. So let me fix some notation. This is my notation for the connected components of this category. Right. Okay, so now let's talk about the homotopy category of pointed curve companies. Pointed. Okay. So the category, so this the homotopy category of the category of pointed curve complexes has the following data. So the objects are pointed curve complexes and the morphisms are this is where this notation comes in hand. So you define that as the pointed component connected components of this category. So that's the point of the notation. And the composition law, so something and make this should be a bit careful about this because you see, so this is like G compose F is equals to G. So you should make sure that we get the order correct. Oops. Oh yeah. I don't want to write this all the time. Okay, so this is our composition rule. So again, what are the homotopy groups of the curve complex? So compare up, see them as follows. So maybe definition. So X again is a vertex, a comparison of X, and you take an element of the X sphere, which is a chosen base point, as we call it. So then the M homotopy group with respect to X, of course. So this X denotes the denotes the sets of homotopy classes of pointed maps. Homotopy classes of pointed maps. And with the group structure, which are briefly talked about later. Right. So, right, again, let me take some more notation. So then kind of make it easy for us to see how why is the sphere come here when we talk about curve complexes. So again, you take A to be a simplicial set. And a simplicial subset B for a simplicial subset B. We write Right. So these are like pointed simplification sets with the base point with base point like this. So, right. So maybe I don't know. So you take, so suppose we have a pointed curve complex and a non-negative integer, and for the set of pointed morphisms, and we identify it's really important to see why the sphere comes in the picture, and we identify with the set of simplicities. Such that if you restrict to the boundary, so it's the constant. So it's the constant. Right. And yeah, like using again typical notations, this is so it's image of right. So this is the notation that I'm using. So this is typical notation. So before we take the pointed curve complex, and again, but this time positive integer. Then there exists a unique group structure. So let's talk about the identity element. With respect to the following structure. So you take the constant map. Right. So this is okay, yeah, this is the image in this. So as I used, as I was talking about this notation. So this is the identity of the now, okay. So take the morphism, which in simplicial sense, right? So it's understood that it's in simplicial sense. So it corresponds to a tuple. So let me call it lambda second of n simplices of x. X. So, sorry, it's sloppy. Okay. And simplices. Now, if so, again, you are restricting it to the boundary. So if it is equal to the constant map, for all i's, and this map, if and only if the product, so we have to find product one to identity and event. Right. So proposition and down. Reality of the constructions. So see how this lets us view this association of homotopy groups as a functor for the Category of time complexes, the Category of groups. Right. So again, you take a morphism between time complexes and from let's fix y f of x. And like obviously for all greater than equal to 1, we have a homomorphism. We have a homomorphism, which we can note right up there. Right. So that takes say lambda or yeah, and simplex of x with its restriction on the boundary being equal to the constant. Being the constant map. Right. So we see that we have a functor between the Category of time complexes and the that is pointed maybe yeah, another pointed time complexes. So that takes Category pointed time complex to right. Cool. So we are almost there to define the long exact. So what is called the long exact sequence of vibrations. That Cisinski calls the Serre's long exact sequence, right? So I'll first define what I mean by a connecting homomorphism. So let me again fix some notation. So let me can name this section as connecting homomorphism. So Y is a time complex, and right. So now we have already X and Y as efficient sites, and this is a time vibration, which I mean obviously implies that X is also a time complex. Now let's fix. So let's fix. Again, so it is same notation. Okay, I think I right. Okay, yeah, I have notation, so so yeah, it's the same convention. But again, if I have already written, so let me go ahead. So it's the fine. Cool. So definition. So suppose it is F is a current vibration in the category of pointed current complexes, and then is a non-negative integer. If we have maps of the meaning this sorry, symbol that I like theta. First one theta, and another one to call it. such that again, so like yeah, so if you restrict one, so you can constant maps taking values x and y. And when you find it, then it does instant. Again, this is find the detail stuff you carried out, but it's mostly gets done by instant. Another simple way. Properly. And yeah, so if you restrict it to the n plus, yeah, if you restrict it to the 0 form, those are connected maps. Taking values. Right. So proposition. Again, if you have this a configuration in the can be a pointed count complexes. Non-negative integer. So you have, so this is the delta that I usually talked about when we saw the long exact sequence that we have of homotopy groups. But so it's unique. Such that yeah, so it's just uses the same notation. Simplifies, but it says that if you restrict them to the boundaries, again the constant values. Constant maps including values x and y. Following incidents is zeta incident. Yes. Here, yeah, I want to do this as I'm already close. I am here to talk about a lot of other things. So this is the connecting homomorphism. So again, you take current vibration in a category of pointed current complexes. Then for all non-negative instances, this map is defined as the connecting homomorphism. Right. So a remark maybe put this. So for a count vibration, with, yeah, n is a positive integer greater than equal to 1. So it's a good polynomial. And so now we are in a position to define the non-exact sequence of the migration. Again, so then you take a down vibration in the category of pointed current complexes. Then the sequence of pointed sets. Pretty sure this is really bad. Yeah. Right. I don't know. It's like right. Is exact. Delta is the way we define delta. I mean, partial. Right. So yeah, so this is the key result of the talk. So yeah, I won't be proving this, but yeah, just so yeah, this is so maybe do a bit, not a lot. So it's obvious to see that you can break the proof into 3 parts. So proof sketch exercises to check that the 3 following sequences are exact. All the ones. Suffices to prove that these are exact. So okay, let me talk a bit about the first one. So just the first one. The first one. Right. So yeah, let's fix again. So you can find all the proofs from the carried out. So this is also from the carried out. So we fix simplex with the fact again that this is constant. Right? So yeah, we want to prove that. So right. So this is what we want to prove. So if sorry again. So this is the image of this map. So I'm talking about the first one. If and only Let's find out. Right. So yeah, the power direction comes from the fact that you have pulling back. Right. It takes there's a constant map taking the right y, so power direction is pretty obvious for the backward direction. So suppose you also do the base point. So we just use the definition. So what does it mean when I say it's a base point by definition? So that means that there exists a homotopy parameter to see how from the dash, which is constant again. Yeah, so when restricted to the boundary. Excuse me, since F is a configuration, it can lift this homotopy. Right. From lambda to lambda. Right. But this is constant. Minor details of each. But then, yeah, it basically follows from here. Yeah, a bit more things right there. So now, okay, now maybe we talk about the right transform or superficial sense. Yeah, we have seen the X and K, so maybe a comment. And I think Cisinski does this properly, but I won't do this. So it's just a comment. So yeah, we've seen the X infinity function before. I think yeah, it was me. Yeah, I was the one who told me. You can prove this. Okay. Now, our proposition. So far, so yeah, we are almost there. I see I'm almost out of my time, so we are almost there. So after this, I'll just define essentially subjective and fully faithful functors, right? And talk about categorical equivalence. So for a weak homotopy equivalence, again, I won't be proving any of these because of the time. For a weak homotopy equivalence, so yeah, let me say this. So yeah, because of the way our talks are structured, so yeah, now gradually as we are moving on, so it become more and more tougher to kind of prove the things because of the kind of stuff that we'll be dealing with. So yeah, can talk about the proofs very after the talk. So okay, let me continue. So for the weak, what are the equivalents of the special set? So also say X to Y. And we'll take another text. If y say x y equals to x, then you have an iso. Right. Moreover, if so not moreover, maybe let me know it as another proposition. So if series are weak homotopy equivalents of special sets, And if we have the following bijection, and this one, right? Oh, then I saw run. Right. So yeah, this is like say like more of a generalization of the transition. So yeah, I want to talk more about this. So now I need to define our fully faithful and then essentially subjective function, and how you can see use them to protect equivalence between greedy categories. So so for so this is a factor between infinity categories. F is said to be fully faithful, which are abbreviated by F. And for all, so yeah, this is just a one category definition. Right. Okay. Now, yeah, like so it is like not an example. So for a factor F from A to B between one categories, F is fully faithful if, yeah, we just take the norm. So it is like the generalization. I can fully the sense that you define it. So a format between one category is fully faithful in the center and the one category presents. Yeah, they're just fully faithful. So now, right. So we're almost there. So now it's essentially factors. So factor between infinity categories, of course. You see the infinity categories is essentially subjective. If so, this is essentially the homotopy category is essentially subjective in the one categorical sense. So what does that mean for all x and t? X, y, t, y, y, so this is what I mean by essentially subjective in the one categorical sense. And this is also true that like so this is also essentially subjective if so if you take the factor between the codes. So that is so say I won't prove anything. So the key takeaway, the upshot, the theorem of the last section is that for the factor again between infinity categories, F is equivalence of infinity categories. If that is fully faithful and the section is objective, proof within the time that I had. So yeah, I think I'll stop here. Thanks for listening. Maybe you can stop recording. Yeah, I think we can stop recording.